before we get started, that bit of the introduction about what this talk is going to be about, I didn't write that anywhere. How did you know? How do you know about the domain expert? Did you read the article, actually? Well, very thorough, impressive. Hi, before we get started, all of you roughly here, you're probably right now coming to the conclusion that you might not have picked the best seat because there's going to be that projector between you and the slides. That happened to me yesterday while I was watching Farad's brilliant talk. You should watch that. And I did not dare move because I thought I was going to be rude and throw him off his groove. So if you want to move to a place where you can actually see the slides, they're quite important to my talk. There's about 700 of them. If you miss one, see, there are other people who are laughing because they don't know me, and there are people who are not laughing because they do know me, and they know that I usually do that amount of slides. So, no, there actually are 700 slides, and if you miss one, you're going to miss the entire talk. So you can move, that's not going to bother me. For the next 5 minutes, I'm going to introduce a talk. This is a good play, it's a good time to move. Right, that out of the way. Hi, I'm Nicolas, and I'm here today because I want to talk to you about, I want to teach you how to implement a programming, general purpose programming language. And I hope you're here because you want to learn that, because otherwise the next 40 minutes are going to be a bit awkward. But I think you should want to learn that. I think you should want to learn how to write a programming language, because first is going to give you a new understanding and insights on a tool that you presumably use most of the day, most days, which is nice. But also, importantly, if you can do the relatively hard task of writing a general purpose programming language, then you certainly can also do the comparatively easier one of writing a domain-specific language. And that can be an absolute game changer when you have to maintain software whose domain experts are non-technical, because it's going to allow you, well, it's going to allow them, really, to write their esoteric and rather specialized knowledge directly to the computer without having to go through you as a rather dubious translator. Also allows you to shift the blame to them when things go wrong, which is always nice. The reason why you should want to listen to me talk about that is because I have implemented a few languages. I'm not going to pretend I did a good job of it. I did a horrible job of it. But I really enjoyed the experience, and I decided to learn how one should actually go about that and implement a programming language properly. Most people would have done that the other way around. They would have learned how to do the thing and then do the thing. Not me, and in hindsight, that may have proven to not to be the right course of action to take. There are a lot of traps, so many traps, and I fell into every single one of them, plus a couple nobody even knew existed. So this is my skill, this is my talent. I fall into traps. I survive to tell the tale, and then I can come here and show you how to actually go about it without falling in the traps. That out of the way, I have shown you, we now know what we're going to talk about, why we're going to talk about it, and why I'm the one talking about it. You may notice how subtly I'm showing you how to do a talk introduction at the same time. And now we can get to the meat of the problem. What is a programming language? The way I like to think about it, a programming language is a set of terms and the rules to combine them in order to express clear and concise instructions to a computer. These instructions are usually found in the shape of text, which we call source code or code. And once you have that code, you send it to specialized software in order to do stuff with. You can, for example, go from code to equivalent code that looks nicer, that's prettier. You'd call that a formatter. You can go from code to semantically equivalent code that runs faster. That would be an optimizer. You could go from code to semantically equivalent code in a different language, and that would be a compiler. Or you could go from code to the result of running that code, and that would be an interpreter, and that is what I intend to talk to you about today. You may have noticed I have been very careful to phrase all these things as functions. You go from code to something. When you're working with functions, it's always very important to nail down your domain and your codomain. And in our case, the domain is going to be code, and we have to decide how we're going to represent code. Now, you may be thinking, he said earlier, code is usually represented as text. Text is traditionally encoded as strings, so maybe we just want code to be strings. But the problem with that is there are infinitely more strings that represent invalid code than strings that represent valid code in any language. So that's just not going to cut it. If you know anything about me and my work, you know I can be a bit of a snob when it comes to types. We're going to need something better. Text is still going to be part of the equation, obviously, because that's the way we, as humans, interact with code. But we're going to pretend that there exists a function from text to whatever representation we're going to use for code. That function is traditionally called a parser. And parsers are extremely fun, interesting. I don't have 7 hours, I have about 35 minutes left, so I'm just going to skip over the parsing entirely. This is not what I want to talk about. I just want to talk about interpretation. Okay, so now we know we want to represent code. How are we going to go about that? So the way I like to do that when I'm working in a domain that I'm not super familiar with is I start off by representing the smallest possible interesting value of my domain. So let's start from that. Let's do that. What's the smallest possible code you could write? A number. It's not interesting. I did say it has to be interesting. That's not interesting because my definition of a programming language was terms, that is a term, and the rules to combine them. We're not combining anything. So let's add addition so that we also know how to combine two numbers together. And that is the smallest interesting program we could write, the smallest interesting expression in the language, which is either a number or the addition of two numbers. And whenever you want to represent something that is either one thing or another, well, you have to use sum types, which in Scala, yeah, the entire talk is in Scala. I try to not show too much code because I know everybody hates Scala syntax, but it should be fairly simple, easy to follow anyway. So expr is an expression of a language, and it can be either a number, which wraps an integer, or the addition of two numbers, which have a left-hand side and a right-hand side. Now, that is pretty straightforward. That is very easy. We are going to interpret that, but before we interpret it, the code for interpreting that is going to be very easy. But we are going to write more and more complicated elements to our language, and I don't want to focus on the code. So the first thing we're going to do is come up with a formal notation to describe the semantics of a language. It's called the operational semantics of a language. We're going to do them for num and add. You're going to think it's a bit overkill. We didn't need that. We don't need that yet. We will in a while. So the way that's going to go is, that says, if you encounter a number wrapping a value, it's going to be interpreted as, well, the only thing we can interpret it as, really, is the wrapped value, right? You have a number, so you return that number. So num is straightforward, it's easy. Add is a little more complicated, but not that much. You have left-hand side and right-hand side, so you want to add them, don't you? But you can't. Those things are not numbers. They are expressions of a language. So the first thing you have to do is turn them into number. How do you do that? You do that by interpreting them. So you say left-hand sides get to interpret to some v1, right-hand sides get to interpret to some v2. And you can see that the rule on top and the rule at the bottom, they have a different role. The rule on top are preconditions. This is saying, if the left-hand side evaluates to v1 and the right-hand side to v2, then the rest is going to be true as well. So we're going to split them. We're going to separate them by using this horizontal line. And now we can say that addition is just the addition of the number that we had. Right? So that was easy. And we can now turn that into code. The way we're going to do that is, well, we are working with an expr, which is a sum type. We're going to return a number or the addition of two numbers, which is a number. So we're going to return an int. And since we're working with a sum type, the only thing we can do really is pattern match on it. And then for each branch of the pattern match, well, if we have a number, we have the solution. Since we have the semantics, we just return the wrap value. It's just there. And for the addition, it gets a little more convoluted, so I'm going to extract that to a different function. And we just follow the semantics. The left-hand side is interpreted to v1, the right-hand side to v2, and we just add the two, and we're done. That is easy. Let's take that for a spin, see whether that works. We're going to add 1 and 2, and as expected, this returns 3. That is not a good test. If we were working together, this was a PR, and that's the only test you had written for your PR, we would have a problem. But for a talk, that'll do. This looks like it worked, doesn't it? We'll be fine with that. And that construction, expr, that I have shown you, it is so useful, such a common construction that it has a name. It's called an abstract syntax tree, or AST for short. Now, what's confusing about it, it's also an algebraic data type. So it's an AST that is an ADT, and people sort of get confused and mix the two. But we're using an abstract syntax tree. And if you listen to that sentence, abstract syntax tree, it's got two elements, abstract syntax and syntax tree. It is an abstract syntax because that expression on top, 1 plus 2. How does it differ from that one? I mean, the syntax is different, but it means exactly the same thing, right? How about that one? Again, it's got white space, parentheses, but they're useless. I mean, they're good for us human beings because it makes the code clearer. But when you load them in the AST, you don't care about these details, so you abstract over the unnecessary details of your syntax. So that would be the abstract syntax bit. How about the tree part? Here's a tree. The operator is the root of the tree, the operands are the leaves of the tree, and you get a tree. Well, I say a tree, it's got a height of 1, cannot grow at all, it's more of a bonsai than a tree really, and that is actually a problem. It is a symptom of a failure in our design, because if I didn't want to do 1 plus 2, but something crazy like 1 plus 2 plus 3, can't do that. Our expression does not allow us to do that. The problem is here. We have said that addition took 2 numbers. It doesn't take numbers, it takes expressions. And if it takes expression, then you can have an arbitrarily deep tree, and then you can have nested expressions, and you have something interesting, and that is what we wanted. So let's fix quickly our interpreter for that. We're not taking numbers with expression. That doesn't need to change. You can pass an expression. That doesn't change either. And everything still works. And then we can fix our test case to include 2 plus 3, and we get 1 plus 2 plus 3, 6. Brilliant, exactly what we wanted. What have we seen so far? We've learned that source code is represented as a recursive sum type. We have learned that it's called an AST, very important, and that ASTs are interpreted through a recursive pattern match. During this talk, whenever you see a slide like that, 3 bullet points and key takeaways on top, that's when you can ask questions, because that's when I'm going to move to a different part of the talk. If something is not clear in what we've seen, you're not going to understand the rest of the talk. So if anybody has a question, now is a good time, and if you don't, I'm just going to carry on. No question. Okay, so we have the premises of a programming language. We have the beginning of one. What we have really is a glorified calculator. We know how to do additions. It's not useful yet. We cannot express anything complex yet. In order to be able to express complex logics, we're going to need the ability to take decisions. And taking decisions is done with a construct, a term that is called a conditional. It goes something like that. I have a predicate. If that predicate evaluates to true, then we're going to evaluate the onTrue branch. Otherwise, we're going to evaluate the onFalse branch. It's pretty straightforward. There's nothing difficult here, so we're going to do the semantics for it. The term, I'm going to call it cond, has a predicate, an onTrue branch, an onFalse branch, and we're going to interpret the predicate. But what do we put here? We don't have the syntax to say which is a true or it's false and what to do. But we do in that I never said we can only have 1 rule. We can have 2. We can do that. That's a rule for true, and at the bottom is a rule for false. And so in the case true, then we do onTrue and we return that. And in the case false, we do onFalse and we return that. So that's, again, pretty straightforward. In order to implement that, we are going to have to update our AST to have a new branch cond with the predicate onTrue and onFalse. And then we're going to have to update the interpreter in that function. And it's, again, we just follow the code. It's the semantics. This is telling us if the predicate interprets to true, then we do the onTrue branch, otherwise the onFalse branch. Except, can anybody see the problem here? Yes?
Maybe it is wrong term.
Well done, yes. I thought nobody was paying any attention. He was paying attention. Right, this is wrong, isn't it? Interpret returns an int. And Scala is one of these sane languages where you cannot use an int where a Boolean is expected. Not all languages do that. Some languages don't really care so much about the truth and have something else called truthiness instead, where you do something like that. So 0 is kind of a false, it's kind of falsy, it's kind of a false value. 1 is kind of truthy, so we're going to do that. We are not going to do that. We're not going to do that because we have self-respect. We're not going to do that because truthiness is evil and should never be implemented. Now, I absolutely hate it, but there's a reason for that. It's just not for fun. When I was an intern, I think about 20 years ago or so, I spent an entire week debugging some code in some obscure language, which I think came up with you yesterday, Delphi. So I was an obscure programming language that doesn't exist any longer, I think, but it's a language in which they had made a decision that 1 meant false and 0 meant true. And I assumed the opposite. It took me an entire week to realize my mistake, to debug that, and then I had to go walk up to my internship advisor to tell him I just spent 1 week flipping 1 to a 0. That was a productive week. That was humiliating. So I do not want to implement truthiness because I do not enjoy torturing interns. Usually don't, at least. So how do we fix that? How do we make that work? Well, see, the problem is we don't want an integer. We want another type. We want either an int or a Boolean. And what did I say earlier about how to represent something that's either one thing or another?
Gotcha.
Were you paying attention then as well? Oh, he's not answering. You use a sum type. Right, so you have value, not very creative, but very descriptive at least, which is either a number or a Boolean. Interpret returns that, and then we have to update things a little bit because, bless you, because num must now return a value.num and not an integer, because the interpreter returns a value. Similarly, for add, we want v1 and v2 to be numbers. And we want to wrap the result in a number. And you might be thinking, well, that looks incomplete, because what happens when either the left-hand side or right-hand side are not numbers? We haven't specified that. And that is the entire point. We only specify what needs to be specified. If we don't find a rule to describe what we have encountered, that means the program was invalid and we should fail. So that's perfectly fine. And then we'll update that. So that's going to get a little messy. Again, Scala, sorry. I'm going to explain that quickly. What we're saying is that LHS is a number called v1, RHS is a number called v2, and then we can just add the two. And if they were not number, if either of them were not a number, then we fail. Straightforward, right? So we have updated that, and we now have everything we need to implement cond. That was completely wrong because, truthiness, evil, all that. And we can just say, well, the predicate has got to be Boolean, otherwise we fail. And we don't need to change v here, because I don't care whether it's a number or a Boolean. I just want a value. And now it's going to read even nicer than before, because if predicate is true, then we do the untrue branch. If it's false, we do the unfalse branch, and otherwise we fail. Right? Clear? Let's try that. I want to run that, except, again, there's a bit of a problem here. Does anybody see it? I don't know how to do that. We don't have a way of producing Booleans in our language yet. So let's quickly add Boolean literals. That's going to be very, very quick because we've done that for numbers already, so that's not going to be very complicated. Boolean wraps a Boolean value, and when you interpret it, you return a value.bool. Straightforward. We add the branch, the variant to RAST, which is a wrapper for Boolean, and the interpretation is just trivial. Right? Okay. So now we can test that. If true, then 1, else 2, and when we run that, we get 1. Perfect, what we wanted. What have we learned so far? What was that section about? That section was about conditional, which are straightforward to support, but they did force us to support multiple types of values. And friends, don't let friends do truthiness. I can't stress that enough, it is evil. We are going to encounter a few other evil things in this talk, but that's the main one. That's really the wrong thing to take, and languages still do that, I don't understand it. Questions? Or, yes, there's a question in the back.
Why did you guys
Can somebody give him a mic? Because I'm sorry, I didn't hear what you said.
What was the question? Let me put it in simpler terms. Why not GADTs?
Why am I not using JDTs?
Yeah, like why not index your term type with the type of the term and then you don't...
I'm not doing type checking yet.
Well, but you kind of are because...
No, well, I'm doing it at runtime. I'm never going to have the time to do that. But the question is, why am I using a GADT? A GADT is an ADT that is, in that case, expression could be indexed, could have a type parameter that represents the type of the value you would get if you were to interpret it. And ultimately, we absolutely want to do that. Absolutely. That's because it's great. It makes the interpreter so much easier to write because you know it can't go wrong. You know that if you have a num, then it will evaluate to a number. You don't have to check for that. So obviously it's interesting, but in order to do that, you have to start talking about type checking. Because you have to type check. You have to type check it to make sure that num adds to num. So you have some notion of type checking.
Not really, right? Because like the same way that you don't start from a string, you start from an AST. I would say it's analogous to start from a GADT representation where it is typed by virtue of being a representation in that representation. The same way as you can't have parse errors here because...
And to that, I'm going to answer, I'm doing the talk, not you. No, but you're right. And so I will not have the time, but I can show that later if you want. The later end of the talk is type checking. So how to go from this untyped AST to a typed AST, which is really fun. And then you do get to GADT. And then you have you know what? Let's talk, because you're getting me all worked up. I want to talk about that, but no, it's not the time.
Okay, sure.
But it's a valid question, and yes, in the end, it is a GADT. Yes.
How do you handle, well, if, for example, how do you make it obvious that some operations are supported for certain values?
The question, if people haven't heard it, is how do I make it obvious that the language doesn't support adding numbers to booleans, for example?
For example, Boolean bully. Well, we have
Oh, right.
takes
I mean,
Boolean.
where is it?
Oh, we check for it being an end. But how do we make it obvious to the end user that you can't add Boolean?
Oh, well, I mean, this is a dynamic type language, so you make it obvious to the end user because you fail at runtime. Which is not good. We're going to do better, eventually. But remember, what we're doing is building it from scratch, bit by bit. So first we want to make it work, and then we want to make it convenient for the user to use, and then we want to make it fast, and then we want to make it beautiful. Right now, we don't even have a programming language yet. So the question of indexing it to make it more powerful, yes, but we don't have a language yet. Why are we not?
That was the issue. It wasn't obvious when done very short.
Is it obvious when you're doing JavaScript?
Yes, and
Well, we're doing JavaScript. Later, we're going to do better. Later, we're going to do Haskell, hopefully. But right now, we're doing JavaScript. We're not even doing JavaScript. We're doing BASIC. We're doing a bad assembly language so far. So that's why. I'm going to go back to where we were. Do we have any other questions, or can I carry on? Yes, there's a question over here.
Are you planning to deal with state and statements later, or just expressions?
I'm just doing expression. Oh, no. You mean state like as in the environment?
Yep.
Funny you should say that. Right, okay. So we now have, thank you very much for allowing me to see into the rest of the talk that smoothly. We now have a language that allows us to express complex expressions. And when the expressions go complex, we want the ability to be able to name the result, to be able to reuse them later. I'm going to call that bindings because you bind a name to a value, and the syntax we're going to use is that. I'm using let here because, like, if some of you are doing Scala, this could be var, this could be val, but in that language, that carries a very strong subtext of mutability or immutability. I don't think mutability is inherently bad. I do think it's inherently complex, and I want to postpone putting that in the language for as long as I can. It's never going to show up. We don't need mutability. So I don't want to put it in the language, so I'm going to use let, which is a very good keyword, which I think is better than var and val, and doesn't have that subtext of mutable or immutable. And that bit of code should be pretty obvious what it does, right? Everybody's clear that this is going to evaluate to 1, yeah? How about that one? That one is a little less comfortable, isn't it? That one is bothering you a little. Well, it could interpret to anything. Some languages are going to refuse to run that. Some languages are going to fail at runtime. Some languages are going to say 1. I don't know why. Some languages are going to say null. Scala says uninitialized, I think. The point is not for us to decide what this should do. The point is for you to realize here there's a problem because there must be a notion of scope. There must be a notion of the subset of your code in which a binding is legal. This is confusing. I don't like confusing things, so what we're going to do is we're going to make that part of the language. Anything that goes after the in keyword is in scope. Anything that's not in the in keyword is not in scope. And so the way you interpret that then is very easy. You have that binding, so you say, as you were saying, you move x equal 1 to the environment, you store the fact that x is equal to 1, and it's going to be a valid binding in the scope. Right? So in the body of the let statement, x plus 2, we encounter x. We know its value is equal to 1, so we substitute that. And then we get 1 plus 2, 3. And once you have fully reduced the body of the let statement, you replace the let statement with its body. So that's straightforward, but there are a few corner cases if you think about. The first one is that. The code is not super interesting. That bit is interesting, however. What do I put in the environment? Am I going to put 1 plus 2, or am I going to put 3? Am I going to put an expression or a value? And this is extremely important. It might sound trivial, but that completely changes your language. This is how you have the difference between, say, Haskell and a camel, for example. Because if you put 3 in the environment, that's called eager evaluation. You evaluate your values as soon as possible, and then you put that in the environment. And lazy evaluation, when you put the expression in the environment, you only compute things when they're needed and not before. And you're probably going to think, surely that does not change. The semantics of the language is going to evaluate the same thing in the end, isn't it? Well, in the absence of side effects, yes, you're right. However, it does have a significant impact on performances. Here, for example, let's pretend that we're doing lazy evaluation. So we have not computed x, we've just stored 1 plus 2. This is true, so we do 1, we never needed x. We never needed to compute x, and if we had done eager evaluation, we would have computed x. So 1 plus 2 is not very expensive, but pretend that this is a connection to a database that is running an expensive query. Why do that when it can fail, when it can be expensive, when it can be long, and we never need it in the first place? So in some cases, like this one, lazy evaluation is far more efficient. In other cases, however, let's say I had x plus x. Well, then I would replace it with the same expression twice, and I would compute the expression twice rather than just one. So there's no clearly better way of doing it. They're both perfectly adequate evaluation strategy. I'm going to pick eager evaluation because I think it's more natural. But I do not mean to imply that lazy evaluation is worse, because there's a few people back there who do Haskell and who will kill me if I say that. So we're going to do eager evaluation. Eager evaluation is when you replace 1 plus 2 with 3, and you store that in the environment, and then you do the interpretation. Now, what about this code? It should be pretty clear what that evaluates to, right? X is set to 1, so this is really 1 plus 1. Now x is 2, so that's 1 plus 2, which is 3. That should be clear. That should be obvious. What about if I take the operands of addition and swap them? Addition is commutative, right? There shouldn't be a problem. If you take a plus b, that should be b plus a. Well, let's run through that. We bind x to 1. Then we go into the innermost let statement. We bind x to 2, so we're obviously going to overwrite the value. X is equal to 2. So that becomes 2, x is still 2, and we get 4. With our current evaluation model, addition is not commutative. And that is a bit of a problem. That's something that you sort of rely on in a language, that you can swap the operands of addition. What we've done is called dynamic scoping. It's just about as evil as truthiness. Some languages still do that. There's a few languages every few years who decide that's going to be a great idea. Anybody does Python here? Anybody lived through the transition from dynamic scoping to static scoping? That was not fun. That was painful. That was such a bad idea. So we shouldn't not, again, one of these things you don't want to do. You do not want to do dynamic scoping. What you want to do instead is, when you see that, you don't overwrite the old value. You do something else. You shadow it. What you do is you create a new binding that, while it's in scope, hides the other one. And that's called either lexical scoping or static scoping. I prefer static scoping because it makes it clear that it's in a position to dynamic scoping, but I think lexical scoping is more common. And now that works. Now it's fine because x is equal to 2. We replace x with 2. And then once we replace the body of the when we replace the let statement, we also pop that binding off. And now x is 1, and we get 3, and sanity has been restored. Right? Okay, so now we know how to do let bindings. Let's do the semantics of it. We need a name, a value, and a body. We're going to interpret the value. We did say that we were doing eager evaluation, so the first thing we need to do is interpret the value. And then, well, we said we wanted to interpret body, but we wanted to interpret body in an environment where name was bound to the right value. We don't have a notion of environment yet. And this is why it's nice to be working with formal semantics, because if it was code, I'd have to type up an environment, show you the code, and that would be confusing. Here I can just say, well, we have an environment, done, sorted. That says, in environment E, value interprets to V1. Right? So now we have an environment. And we said that we wanted body to be evaluated in an environment, in the same environment, but in which name had been bound to the value, for which I'm going to use that syntax. Name is bound to value, to V1 in E. And then, well, the answer is just V2. Right? And I like this notation because it makes it very clear the decision we have taken. The first one, eager evaluation, that's right there. We are interpreting value before putting it in the environment. So that's clearly eager evaluation. And this is clearly a syntax for creating a new environment based off of an existing one. So we are not mutating the environment, which would be dynamic scoping. We are creating a new one in which we shadow the value. Right? Cool. Well, of course, we also need, when we encounter a variable, a binding, we need the ability to get it from the environment and to dereference it. So I'm going to call that ref. It's just got a name, and that interprets to whatever the environment says it has for that value. Right? Okay. So let's update the AST. That's going to be easy. Let has a name, a value, and a body. Ref has a name, and of course, the two names must match, otherwise you're going to have some sort of runtime failure. And we need to code up the environment. But that's not very hard. The environment, so you may have noticed it was very intentional, the kind of words I was using, pushing something in the environment, popping something off of the environment. Clearly, I was using stack-based vocabulary. Clearly, that is a stack. So in Scala, a stack is a const list. It's just a list of bindings, where a binding is the product of a name and a value. And I said I needed the ability to look something up. So given a name, I'm going to find the first binding with that name, return that, or fail if it doesn't exist. Creating a new binding, well, I create a binding, push it on top of the stack, and create a new environment with that new stack. And then we're going to create the ability to give users the ability to create an empty environment, because that's just good manners. And now we can write the interpreter. So first, let's do, well, we have to pass E everywhere now because interpretation is done with an environment. So we just pass E everywhere. And then we can do let. Let go like that. We interpret the value, we interpret body in the right environment, and that gives us a result. So all that for that very small amount of code. But now we know exactly why we got there, because we spent the time to analyze it, to formalize it, and now it's trivially straightforward. Dereferencing is just look it up in the environment, whatever's in there, that's fine. Let's try that. So if you remember, that's the thing that returned 4 if we had implemented dynamic scoping. If we run it now, we get 3, which means we have gotten static scoping right. This is exactly what we wanted. What we've seen that local bindings have a scope, and that scope can be analyzed statically. They can be shadowed, never overwritten, and the interpretation requires an environment which you had to code up. So this is one of these, yes?
Quick question. Since you're anyway doing something that's very minimal, would it also be possible to do something without an environment, but just substitute the value into the body? I'm just wondering.
No, we could do that. I didn't want to do that because it is quite painful.
Yeah.
The code for that, I mean, I have written it because it's either one or the other. And doing what you just suggested, the code for that would be quite a bit bigger. I'd need a lot more support function for exploring the AST, finding all the right ones, making sure that I'm replacing the right one, because X can be shadowed, right? And I don't want to replace the right X. So I didn't do that. Although it might have helped with recursion if we had the time to get there. But yes, it's definitely possible to do that. It's more expensive and it's harder to explain. So I have chosen to not do that.
Yeah, thank you.
Cool. Any other question? No, okay, let's continue then. How much time do I have left?
10 minutes.
10 minutes, okay, we're not going to finish. The next bit, what was it? Right, yes, so now we have the ability to name things. We have the ability to name computations. What would be even better than the ability to name computations in order to reuse a result is to reuse computations themselves, to reuse code. Good, see, this is a bit frustrating to me. I don't know about you, but that says, for any x whatsoever, I'm going to give you x plus 2. For just any x, provided that's 1, and I'm not going to do it for anything else. This is a bit frustrating. If we write something that should work for any x, then we should be able to pass any x, not just the one we said here. So what we want to do instead is something like that. The function, which maps x to x plus 2, applied to value 1. We're saying exactly the same thing. However, we have declared a function that can be reused, which is a lot nicer. Now, how does that interpret? Well, so the function and the argument, sorry. So the way we interpret that is, this one is a little bit more complicated than usual because I'm doing two things at the same time. The first thing I'm doing is I'm mapping the function parameter, x, to its argument 1 and moving that to the environment. And the second thing is I'm replacing the entire function application with the body of the function. So that sounds complicated, but it means I'm just doing that. Right? X is equal to 1, and we're evaluating x plus 2, which gives us 1 plus 2, which gives us 3. Right? Straightforward. That's pretty easy, but I mean, last time I explained that, somebody complained. I We're functional programmers. We work with functions all the time. That's our tool in trade. We have functions. We love naming our functions. We love giving them meaningful names that people can use to understand the code that we're reading. We must be able to call our functions F and sometimes J, and if you're feeling really frisky, sometimes we even go to them H. Well, we can do that. We've just spent half an hour finding out how to name things, right? We can use lead binding to do that. But very sneakily, I have made a major language design decision here. Can anybody tell me what it is? Come again? Well, indirectly, what I wanted to say here is a lead binding. Sorry, so here I've bound this function to the name f, and then I can reference it. I have bound a function to a name. But lead bindings, they bind values to name, right? We've just decided that functions were values. We are doing functional programming in the original sense, the meaningful sense, the one which just says functions are values, not the boring things have to be monadic, modern way of talking about functional programming. We're doing a functional programming language, so we're not doing assembly any longer. Right, okay, so since functions are values, we need to update the value type, just a function which contains a parameter, and the body of the function. And that did my head in a little when I first wrote that, because you have a value that contains code, you have a value that contains an expression of the AST. It seems to be sort of so the AST allows you to get values, but some of the values contain bits of the AST, but it makes sense, right? It's a function, it is code, it's something that you're going to run, so the value needs to contain the code. Hope I haven't lost you here. Right, okay. What do we think this evaluates to? Let's quickly, y is equal to 1, so that's really saying the function that map x to x plus 1, we're applying that to 3, that should be 1 plus 3, which should be 4, right? Well, we've made a critical mistake here, and dynamic scoping is back. Look at that, y is equal to 1. We map f to that, and then we shadow y with 2, perfectly fine. Shadowing should keep dynamic scoping at bay, right? However, once we get there, we do the switcheroo thing, we get 3 plus 2, and that is 5 and not 4. That's not the result we expected. And the problem, and this is critically important, that is an extremely common mistake. The problem is here. Y is equal to 1 when we interpret f, when we declare f. When we apply it, somebody created a new binding, right? But that new binding should not be in scope when we apply f. We must apply a function in the environment in which it was defined, not in the environment in which it's being applied. And that is extremely important. I lost days working it out. So now functions must contain the environments. They must do something that you might have heard. They must close over the environment. They're closures, that's where it comes from. And now we can do the semantics, now that we have found all the traps. The first thing is fun, which is a function literal. It's just declaring a function, so there's not much to it. It's got a parameter and a body, and what we do is create a fun value, and we must not forget to close over the environment. Application is a bit more complicated, but not that much. Apply has a function and an argument. The first thing we're going to do is we're going to interpret the function and make sure it is a function, because it could be a value.num, and you don't apply a number to a number. That doesn't mean any sense. So we need a function, and we know the environment in which it was defined. It's e prime here, right? So we have that. Then we said, interpret the argument, makes sense. We're going to need the value. Yes, oh, haven't, yes. And now we're going to interpret the body, but in what environment must we interpret the body? We said e prime, right? But it's not quite right. It's e prime in which we have bound the parameter to the argument, right? And that's it. And now we have the right thing. So we can just yes, v2. Now we can update the AST and write the interpreter, but it's all very straightforward. Function has a parameter and a body. Application has a function and an expression. Interpretation is, where am I? Yes, okay, yes. We're just declaring a function literal, so we just return the value.fun. And without forgetting to close over the environment, again, that is the important bit. An application is going to be interpretation of the function. If it's a function, then we interpret the argument, do the whole thing we said we were going to be doing, and get the value.
Well, the function is expression.
Oh, because you don't have a function in your ST, you have an expression. Oh, the question is, why here is fun of type expr and not of type fun? Because there, apply has an expr, not a function. Well, yeah, because it could be a variable, for example, right? You don't necessarily have a function. You might have a variable, so you have to dereference that. And that is the beauty of the AST. It's recursive, so you could have a function that defines a function, that returns a function, etc., etc., and that's all interpreted, pushed back up, and you just... Okay, sorry, I was getting excited about it, because I find it really cool. Okay, where were we? Oh yeah, so basically it works, right? The last thing that I want to talk about with regards to functions is some people might complain, we've only done functions that take one argument. We've only done functions of arity1, and there are so many functions that take more than one argument. For example, addition. Addition famously takes two arguments because you add two numbers, right? Well, it's just a matter of perspective, however. Because if you think about it the right way, add could be seen as a function that takes the left-hand side and returns a function that takes the right-hand side, and that returns the addition of the left-hand side and the right-hand side, right? That is called, do we say currying or curryfication? Currying, right? Currying, yeah, that one, currying. So everybody knew that, perfect. You could have stopped me before I spent all that time explaining it if you all know it. And that all works. Now, when we run addition, the body of that AST is just massive. Trust me, that's the right body there. And we get 3. So what we've seen that functions have values, they close over the environment, and yes, unary functions are entirely sufficient. Now, we have 2 choices at this point. The first one is we can obey the rule and stop here. Or is there a talk after, or is it a break?
Wow.
Oh, and you want to go there quickly because there's going to be a massive queue, right? So you decide. I could keep going. The only last thing I wanted to talk about is recursions. It should take about 5 to 10 minutes. I'm also fine stopping. Or anybody who wants to go have lunch, go have lunch. Anybody who wants me to keep talking for another 5 minutes, stay here. I'll keep talking.
No.
All right, where was I? Right, okay, so we have just about everything we need for a full programming language. Not all the bells and whistles, but all the bells and whistles are built on top of what we've done. Once we have that, we have a full programming language, except we're still lacking one thing, the ability to repeat actions. Typically, repeating actions would be where you have a range from a number to a number, and you want to add all the numbers in that range. With the tool that we have at the moment, we can't do that. That's the last thing we lack. And, well, in traditional mainstream languages, the way this is implemented is typically by using loops. So, for example, we could use a for loop, which works like that, right? You have a lower bound and an upper bound, and you would create an accumulator. Notice var, eminently mutable. I don't like it, but for for loops, we have to have mutability. And then you would iterate from the lower bound to the upper bound, keep the value in I, your counter, which is incremented at every iteration. You increment the accumulator with that value, you update it in place because it's mutable, and then in the end, you return the fully mutated accumulator. That works. I have 2 problems with it. First problem, I've been pretty heavy-handed. I don't like mutability. If I can avoid it, that relies inherently on mutability. So that's a problem we're going to fix a bit later. The other problem is an inherent flaw or limitation of for loops is you need to know the number of iterations you're going to do in advance. And that is frustrating. You might have, for example, to empty a queue, and you don't know how many iterations they're going to take. What you want to do is just pop off an element of the queue and then keep doing that until it's empty. You don't know how many iterations you're going to do. Luckily, there is another kind of loop that allows you to do that, which is called a while loop. And a for loop can be automatically translated in a for loop. No, the other way around. A for loop can automatically be translated to a while loop. I'm not going to prove that. A, I don't have the time. B, I don't know how to do it. I just know that somebody smarter than me proved it, so you can look that up. I'm just going to give you the intuition, however. Let's rewrite that as a while loop. See, the thing is, here, for is creating a variable called I and keeping it up to date for us. It's just a convenience, but we can do that ourselves. We can just say, right, I'm going to do I, which is initialized to lower, And then I'm going to increment I by 1 in every iteration. And then that is just really a test to make sure that we don't go over upper. And that's it. We have turned our for loop into a while loop, and we can have the parser do that for us, right? The parser can do the whole thing. It encounters a for loop and translates it into a while loop. So if we have while, we don't have to implement for. So we're just going to implement while. But we still have a problem with while, eminently mutable again, but there is a way of removing the mutability. Since I mentioned recursion maybe 5 times already, it's pretty clear what we're going to be doing. We're going to do a recursive version. Recursion is when a function calls itself. And here, this helps, because really those two things, we are making them mutable, we are keeping them as variables, but what if each iteration of the loop was another function call in which we pass the updated values for these two things? What if we did that? Right? We remove that, turn that into a function, which traditionally is called go or loop or something like that. I prefer go, so I'm using go. And this is really saying stop when I is smaller than upper. So let's do that. When I is not yet smaller than upper, I do one more iteration with the updated values. And when I'm done, then I return the accumulator. Right? So you can transform automatically a while loop into a recursive function. So if we have recursive functions, which do not require mutability and do not have the limitation of requiring you to know how many iterations you're going to need to go through, we have while and for free. So we can do that. We can implement recursive functions instead. Before I do that, before we go, I want to make that a bit better, because that works, but that code is an abomination. When you do recursive code, what you really want to do is do declarative programming, where you describe the problem and that magically turns into the solution of the problem. Works like that here. This is saying, if the range is empty, then the solution is 0. That makes sense, right? You need to say that. If the range is empty, the solution is 0. If it's not, however, then the solution is the addition of the first element in the range to the sum of the rest of the range. And that, I find that beautiful. I find that grand. Just the description of the problem is a solution to the problem itself. This is, anyway. So that looks a lot like something we could run already in our language, except we don't have this operator, so I'm going to implement that really, really quick. I'm way over time, so just pretend you've understood all that. It's basically the add, There's nothing complicated, right? You want the left-hand side to be V1, the right-hand side to be V2, and then you compare them. Right? We've done that for add. There's nothing new here. It's boilerplate that I have to write, but it's nothing we haven't seen before. There we go. What we haven't seen before, though, is that this doesn't actually work. When you run it, it's complaining that the sum binding doesn't exist. Why is that? Look at that. The binding is telling you, I'm going to bind the name on the left-hand side to the value on the right-hand side. So the value on the right-hand side is interpreted before the name exists. So clearly, it cannot reference sum, and yet it does, before sum exists. So we have a problem here. That can't work. Let is not a sufficiently powerful tool for our problem. What we're going to need instead is something called letrec, for recursive let, which is going to look a lot like a let, except it's going to allow us to do recursion. The way it's going to work, here, function declaration, we capture the body of the function and the environment. So we capture the environment. We don't use it, though. Not until we do the application, much, much later. So there's a window of opportunity there. We have created the value, we have interpreted the value, captures over the environment, and then now that we have the value, we could go in the environment and update it to the right value. I am in fact talking about mutability, but it's not in the language. It is in our interpreter, but we don't have a single mutable primitive in our language. But we are going to need them in order to do the interpretation. So what we're going to do then, letrec, the semantics. We have a name, a value, and a body. The value, well, we want to interpret that, but as I said, we're going to mutate the environment. And if I'm going to use E here, I'm going to use somebody else's environment. And if I mutate that, I'm going to break absolutely everything. So what I want to do is clone that environment. The only primitive we have so far for cloning an environment is to create a new binding. That works out well for us because we do want to create a new binding of name. Of name to, well, we don't really know what yet. That's the entire point, isn't it? We don't have that value. So we're going to create that binding to null. We are doing both mutability and null, and isn't that just fun? And So this is going to be interpreted in E prime. And now we're going to interpret body in E prime. But before we do that, however, we must not forget to loop the recursive loop. We must not forget that E prime must be updated in place to have the name point to the right value. That's syntax for update in place, right? Okay. And then the result is just V2. So we said we need to update the AST. So let rec looks a lot like let, because it's basically let with different semantics. And we also need to be able to update the environment in place. Well, that's easy enough. You can just add update. You look for a variable. If you find it, you update it. In order to be able to update it, we just need to make sure that the environment is mutable. That's all. We're done. Now we can write the code of the interpreter. We're going to do let rec. And after all that work, it's surprisingly easy, because all we do is we create the environment as we said we would. We interpret the value inside of it, do the binding, interpret the body, and we're done. And if we test it, we get, well, that rec, of course, and the sum of 1 to 10 is 55, which is the result that we get here. So this all works. And what we've seen then is loops are implemented as recursive functions, which allow us to support all loops known to man. Recursive function need a special syntax and a mutable environment. Now, if I had another half hour, don't worry, I'm not going to do it, but if I had, I would start talking about types and type checking and GADT, as the man who's not here any longer mentioned earlier. So instead, I'm going to close. In closing, if you only remember just one slide, this is a slide to remember. Programs are represented as ASTs. We use formal semantics to reason about them, because these formal semantics don't have all the noise of a programming language. You can think about them very clearly without all those tools that get in the way. And once you have the formal semantics, implementation is then relatively straightforward. Now, there's still a lot we could do here, but the language that we have is enough. With these primitives, it can be proved that we can interpret we can write any program. It's not going to be fun. Representing a list with what we have now is not going to be fun, but we could do it, for example. It's just function call. We could do touch encoding, for example. Very painful, not fun at all, but doable. We have the smallest possible interesting programming language, which is cool. Now, what I'd like to talk to you about, if I had the time, were, at the moment, we could do stupid things like adding numbers to Booleans. And I'd like to be able to check that beforehand. I'd like to be able to write a function that makes that impossible. In fact, I would like to have an AST that makes it impossible to do such things, the GADT that we talked about before. I would like to do type inference, because if you're talking about type, then you have to have type annotations, and if you have type annotations, well, now that you can write them, you don't want to write them, you want the compiler to infer them for you, so you need type. All these things, super exciting, very, very fun. I've been talking far too long already, so instead what you can do is go read about them in the articles I wrote on the subject. And in the meantime, I'm happy to answer, well, I don't have the time to answer any question, but go have lunch, and if anybody wants to chat, I'm right here.
Thank you.